Let me thank the organizers for inviting me here for a lecture. It's a great honor, as well as a big pleasure standing here describing work that we have been doing in the past few years. I'll talk about X-ray absorption spectroscopy on catalysts that are under pressure. I will talk about how the structure of a catalyst is a function of its pressure, and what is the actual consequence of that in understanding catalytic processes. So what's a catalyst doing? Basically, a catalyst breaks bonds and makes bonds. And if you look to the catalytic process, there's a few essential steps that a system needs to undergo for a catalytic process to occur. First of all, reactants need to adsorb on the surface of the catalyst. So there's bonds being formed with the catalyst. Yeah, intermediates are formed. Second step is the surface reaction, where you can see it's a surface reaction that occurs. And of course, if the new products are being made, they need to desorb from the surface of the catalyst. Yeah, so there's three fundamental steps: adsorption, surface reaction, and desorption. If you then look to the catalyst, catalysts often have multiple components. Very often there's not a single site that does the trick, but there's multiple locations at catalysts that have a function within a catalytic cycle, in the catalytic process. And of course, it's very interesting to understand what those sites are, what the phases are that are active, what component in a catalyst has what kind of function. If you look to industrial processes, for example, methanol synthesis, where I will talk about today, they are at elevated temperatures and very often at high pressure. Ammonia synthesis, Haber-Bosch, very well known, that's a high pressure process. Fischer-Tropsch is at elevated pressure. Water gas shift, that's done at elevated pressure and temperature as well. So if you want to understand the catalytic process, of course it's interesting and it's essential to look under the conditions where the catalyst is actually doing its function. And of course I have to say that an industrial catalyst is a very complex material. It's not a single surface, it is a material that has been processed. There's multiple functions in there, far beyond just a catalytically active site. And of course, and I'll come back to that in the end of my talk, we need to understand all aspects of a catalyst to really appreciate the catalytic process in an industrial working system. So I alluded, and of course in the catalytic community, in situ and operando characterization is something that has been introduced and is very widely used. And the reason that it is so is that a catalyst structure is a function of its environment. So under vacuum conditions, the surface may be perfectly organized, but in the presence of reactants, a surface may look very different. And then you come to the premise that only the structure that is measured under reactors' relevant conditions can give you insight into the activity. And of course, one thing to keep in mind here is that if you have a catalytic conversion, the catalytic conversion per se is changing the composition of the gas phase that the catalyst is seeing. So within a single catalytic reactor, very often there is different places within the reactor that sees different gas environments, and that may have, and in some cases it has been shown, has an effect on the structure of the catalyst. Of course, the pressure gap is a well-known phenomenon. But if you look carefully, there is relatively few studies that systematically bridge the pressure gap and try to understand what the effect of the pressure on the surface of a catalyst is. And that's where I will spend the first part of the talk. In the second part, I will describe the consequences of the findings that we have on that. But first, some background. As I said, catalytic reactions, adsorption, surface reaction, desorption. The surface of a catalyst is really a function of the conditions. And to illustrate that, I show you some very simple examples of a Langmuir isotherm where, as function of pressure, I look to the coverage on the surface. A typical example of hydrogen on a metal surface, yeah, as function of pressure, the coverage at relatively low temperature, the surface at relatively low pressure will be fully covered. But of course, if you enhance the temperature, the coverage will be less. So depending where you are in the pressure temperature regime, you really have a different surface coverage on the surface. If you now plot the same thing as function of temperature, yeah, for different pressures, if you work at very low pressures, of course, yeah, at very low temperature, there is nothing at the surface anymore. Yeah, and if you increase the pressure, there is an enhancement of the surface coverage. Very simple considerations, but those considerations have huge impact for understanding how a catalyst actually functions. And of course, there are different bond strengths on the surface, yeah, and then here there is the coverage as function of bond strength. So if there is a very strong species bonding, yeah, at very low pressure of such species, yeah, there is full coverage on the surface. And of course, that's why poisons that strongly bond to the surface of a catalyst are actually very hard to get rid of because they bond so strong at the surface and you don't need much pressure to actually kill whole surfaces. Yeah? Weakly bond species, the coverage of those species is relatively low. And of course, I can do the same thing here, where you look as function of temperature, what species do you have as function of bond strength, and then you can see that the strong bonded species, of course, they are desorbed at much higher temperatures. So keep in mind, the surface of a catalyst is a function of its conditions. But of course, that's just adsorption on the surface. And here I give an example from the literature, where there is theoretical prediction of what a surface looks like in the presence of oxygen and carbon monoxide as function of their pressures. And of course, you can see that there is very different phases present at different conditions of the measurement. There is phases where there is carbon monoxide only on the surface. There's different arranged surfaces. There's mixed phases where there's both oxygen and carbon monoxide on the surface. And there is oxidic surfaces. And this really depends on the pressure of the gases. So this means that the pressure gap is actually a materials gap. You have different materials under different conditions. Then there's a final consideration. If there is multiple reaction mechanisms possible in a catalytic reaction that have different orders in the reactants, so here is the predicted rates of reactants as function of pressure for different reaction mechanisms would have a different order. You can see that the reactions with the different order at a different pressure regime, they are the most active. So there is maybe changes in the reaction mechanism just based on such simple considerations. So not only is the surface a function of the conditions, but also the reaction mechanism may actually change as function of pressure. So then I move into a more practical system. This is carbon dioxide hydrogenation into methanol. Why is this an interesting reaction? Well, you have to come to this conference and you'll see this is very much studied system because there's environmental concern because of CO2. And hydrogenation of CO2 into methanol is a route for making chemicals and fuels out of carbon dioxide. If you have the methanol to olefins to chemicals or to fuels, those are existing reactions that you can actually exploit to make chemicals out of carbon dioxide, provided that you have clean hydrogen, of course. And very interesting, also for us, there's a big scientific debate about the structure of the catalyst and the reaction mechanism in this system. So the question that I will address is the following. The reaction is done in a multi-component catalyst, and can we assign the function of each of the components in the system? So I will look at the copper zinc oxide alumina system, and secondary I will look at palladium on zinc oxide for this reaction. So I look to the copper zinc oxide on alumina system first. There is many different proposals what are structures of catalytic active sites. There is the copper surface that does the hydrogenation. There is copper zinc alloys zinc atoms in the surface, patches of zinc species on the surface. There is the copper-zinc oxide interface, and there has been a role of the zinc oxide in this system that provides catalytic activity. The beauty of this system is that a copper-only system is active for this reaction, as well as the zinc oxide-only system is active for this system. However, if you combine them in the right way, the activity way goes up. So here, the multi-components really lead to a synergy, to a much higher catalytic conversion. And of course, it's very interesting to see, to try to understand why this actually is and how this functions. So I'll talk about the pressure gap, and I will look at the structure of this copper-zinc oxide on alumina system as function of pressure. I will compare the different components that we have. And in the second part, I will go to the methanol synthesis from carbon dioxide. So under catalytic conditions, I try to identify the different structures and try to relate those to catalytic conversion. So the copper-zinc oxide on alumina system is a rather ill-defined system, where copper particles are attached to zinc oxide particles. There's patches of alumina around. It's a very diverse system, which does not really have a perfect, well-defined system. If you look in more detail to the copper particles, there's twin boundaries. There may be overlayers on the surface. So it's directly clear that very preliminary simple characterization shows that there is a very high diversity in the structure of this catalyst, which of course makes it very difficult in trying to assign catalytic structures and relate structure to performance. So as I said, there is many different proposals. There's a lot of discussion in the literature about active sites, and here I list a few of those. And I could add more, but there is really no consensus on activity-structure relations in this system. I would say the copper-zinc is a prototype for a multi-component catalyst, but it is really poorly understood. So if I highlight a bit of literature, where there is, as function of pressure, in the pretreatment of this catalyst, which is a hydrogen reduction. So on the x-axis here, there is a pressure of the hydrogen that's used during a pretreatment. And on the y-axis, on the bottom, it's the zinc ratio in a copper surface. And on the top, it's the copper surface that is free for adsorbates or that you can detect in XPS. So what is obvious is that the copper surface goes down as function of the hydrogen pretreatment pressure, and the amount of zinc that's at the surface goes up with the pressure in the hydrogen of the pre-reduction. So really there's a very strong dependence of pressure on the actual surface that you will end up after a pretreatment reaction. So what we looked at is systematically to the structure copper-zinc oxide as function of the hydrogen pressure, and a good technique to use for that is X-ray absorption spectroscopy. The beauty of X-ray absorption spectroscopy is that the X-rays, they have very large penetration depth, so I can put an actual catalytic reactor in a beam. I can measure my structure while I'm performing my catalytic reaction. And here what I will show you the temperature programmed reduction profiles at different pressures. So we do millibar range up to 10 bar, and nowadays we can go even higher than that. So we're bridging 4 orders of magnitude in pressure, and we simply look to the structure of both the copper and the zinc. Because copper and zinc are neighboring in the periodic table, the X-ray absorption, you can virtually measure the X-ray absorption spectrum at the same time. So you're scanning through the both edges at the same time. So you really have the structure simultaneously measured under exactly the same conditions. These measurements are done at the superexcels beamline, which is really a beamline for time-resolved X-ray absorption, and it's specialized for, amongst others, for catalytic research. So this experiment is relatively simple. We have, as function of time, we have a heating ramp, and then we measure 5 degrees per minute at different pressures, and we measure the copper and the zinc oxide structures. So on the left is the copper K edge, Yeah, so we're measuring while we're heating the sample, and on the right side is the zinc oxide, is the zinc KH, yeah, and they are measured virtually at the same time. Yeah, you can see that there is a certain structure, and because X-ray absorption can quantitatively define the structure that you have, and you see at a certain temperature there's quite a few drastic changes occurring in the copper edge. Yeah, basically you go from a copper 2 oxide, reducing this into copper 0. And at the moment that the copper 0 is actually formed, that's where the large changes are occurring in the zinc spectrum. So we've done this experiment for all the different pressures, and I'll show you that in the next slide. And on top is the lowest pressures of hydrogen, and on the bottom it's the higher pressures of hydrogen. And now the color of the spectrum represents the temperature. You can see things occur at very different temperatures. But the changes that occur are relatively similar. In the zinc edge, things are much more drastically different. Yeah? There's relatively minor changes in the zinc K edge at low pressure, yeah? while the spectra that are measured at much higher pressures show much more drastic changes, so the structure of the zinc is much more sensitive to the pressure, yeah, than that of the copper. As I said, we can quantify our data, yeah, and at the bottom we have the quantification for the lowest pressure, yeah, where the initial spectrum show that there is a copper 2 oxide, yeah, and the moment that the copper 2 oxide is reducing, yeah, there is a copper 1 oxide phase, which is an intermediate, and this will actually transform into a copper 0. If you now increase the pressure, yeah, this will occur at a lower temperature, yeah, so there's an order in the pressure of the reduction, yeah, and you can see that the amount of intermediate that you make is decreasing with increasing pressure. Yeah, so the rate of the copper 1 oxide reduction is much faster, yeah, and you can see it, you can hardly see it anymore at the higher pressures. So we can do the same quantification of the zinc spectra, yeah, which is much more difficult, yeah, except for the spectra at the lowest pressures, yeah, where there is, at the starting material, there's a mixture between zinc oxide, yeah, and zinc hydroxycarbonates, yeah, and then there's a small increase with increasing temperature. There's a small increase in the amount of zinc oxide and a decrease in the amount of the hydroxycarbonate. Yeah. At the temperature where the copper is reducing, yeah, there's a large shift into structure, yeah, where zinc oxide is fully formed. Yeah, so at the lowest pressure, we have a system where we make copper particles, yeah, connected to a zinc oxide phase. If you increase the pressure, yeah, this happens at lower pressures, yeah, and then at a certain pressure range, we see at a specific temperature, yeah, we start seeing changes in the zinc spectra, and they are indicative of the forming of a reduced zinc oxide phase. And only at higher pressures, yeah, do we see in the EXAFs a feature of metallic zinc copper phase appearing. Yeah, so that means that at a certain pressure, zinc oxide is reducing. And this still occurs at the higher pressures, but the reduction is deeper, and there is the formation of an alloy, yeah, which is detected in the EXAFs of the zinc. Yeah, so we have, as function of temperature and pressure, there is a strong dependence on structure. The copper zinc alloy we only detect when we use pressures above 1 bar. Of course, this is relatively trivial. If you like to reduce something and you have 1 millibar of hydrogen pressure and it doesn't reduce, what do? You increase the hydrogen pressure. If it doesn't reduce at room temperature, you increase the temperature. So it's rather trivial. However, the consequence of this is enormous. Now, if I now make a plot where I plot the different structures, yeah, in different colors, yeah, we get what we call the rainbow plot. You can see this function of temperature and pressure, we have very different structures. So if you want to have a good representation of a copper zinc oxide system and you're interested in a model system, of course the question is, what's the model that you choose? And the second question that comes, if you have a model system, you know, where does the structure go under what conditions? And based on this relatively straightforward study, the choice of this is very difficult. We need to be careful and we need to really understand what is the regime, where am I, what is the structure that I will make or what the system will go, under what conditions that you have. So keep in mind, different structures under different pressures and temperatures. So the copper zinc oxide on alumina catalyst is very sensitive to the hydrogen pressure. Copper 1 oxide is a short-lived intermediate, which you can really detect at the low pressures. At the high pressures, it's hardly detectable. We do not see any copper zinc alloy formation below pressures of 100 millibar. And there is a reduced form of zinc oxide prior to brass formation. Again, different pressures yield very different structures. So now we go to carbon dioxide hydrogenation. So what's the structure of this catalyst and where will this structure go under catalytic relevant conditions? I talk about pressure, so let's look at the pressure, the thermodynamics as function of pressure. So on the x-axis, there is the pressure of the system, and on the y-axis, there is the equilibrium methanol yield that you can achieve. It's an exothermal reaction, and the dashed line, that's the carbon dioxide system, and the solid line is the CO-based system. But they, of course, because they're both exothermal, they show the same trend. The lower the temperature is, the higher the equilibrium conversion, and of course, because you have more reactant molecules than you have product molecules, pressure is in favor. But it really shows that if you go to low pressure regimes, you do not make much methanol. And of course, that is why this is a high pressure reaction. Simple considerations, but essential for trying to understand what the structure of a catalyst is. So I'll try to look at the different components, what are the structures, and I will look at the copper zinc oxide on alumina again, and I will look at palladium on zinc oxide. And then the big question is, what's the role of the zinc or the zinc oxide in the system? And is there a role of copper zinc alloy, and is there a role of the palladium zinc alloy in this reaction? So we try to ask ourselves, what's the reactive species that we have at the surface? And for that, we combined acidca and Fourier transform infrared. And in the acidca, what you do is you have a rapid shift, switch of a molecule, and you change an isotope in the molecule. So where we have carbon dioxide, carbon 12, we have a rapid switch of carbon dioxide with carbon 13. And of course, it keeps the pressure in the system constant. And in a mass spec, you can see how fast is the system responding. So how fast is my main product, methanol, and how fast is my side product, CO, coming off the system. And of course, if we look with infrared on the surface, we can look at the intermediates. And then because infrared is sensitive to the isotope, you can see band shifts in the system occurring in the intermediates. And you can see how fast are the intermediates actually exchanging, and is this relevant for the product methanol or CO that we see. So what we do, we have this experiment at 15 bars, 260 degrees. We have still the same copper oxide, zinc oxide on alumina system. The hydrogen CO2 ratio is 3. And here I'll show you the Fourier transform response. So this is the different spectra that we measure. So we have the switch of carbon 12 CO2 to carbon 13 CO2. And what you can see is that there is a band which is decreasing rapidly. That is actually the formate carbon 12, and instead of that we have the formate carbon 13 coming up. And then you have the asomatic shift and you have the somatic shift, and they have a full interconversion. If you look to the mass spec response, which is in the same system, the measurement, there's the rapid appearance of carbon 13 CO2, and very interesting, CO, carbon 13 almost directly forms, and then there's the methanol carbon 13 that has a delay in the system. But it's really the formates that are the primary products, and they will undergo full interconversion during the isotope switch. So we see in our system, under our conditions, the formate is the intermediate that actually the precursor for methanol. So if formate is a reactive intermediate, the next question, of course, is where is this formate? Is it on the copper? Is it on the zinc? Or is it on the alumina? because we can measure the copper and the zinc, yeah, and then we measured under these conditions very similar the X-ray absorption spectra. So what we have here, we measure at 15 bars, 260 degrees, so exactly the same conditions. The ratio of hydrogen CO2 is still 3, and we have a transient switch between pure hydrogen and carbon dioxide and hydrogen, and we can of course switch back and forth. And then we look time resolved to the spectral change that we have, and that we can transfer back into structural speciation what occurs. If you look to the copper K-edge, rather not well, very interesting, but not exciting, yeah, because the spectra are the same. Yeah, they're not sensitive. You have reduced copper after reduction, and if you switch to hydrogen and carbon dioxide, you still have reduced copper particles. If you look to the zanes, there the changes are much more significant and severe, and we can quantify those, and that's done in the figure on the right, yeah, where most of the zinc is present as a zinc oxide phase. Yeah, and part of it, after the reduction at this relatively high pressure that we did, yeah, there is zinc-copper alloy in the system. The moment that we switch on the carbon dioxide, yeah, so we have now going to switch to hydrogen to carbon dioxide, hydrogen, catalytic conditions, that's where the conversion starts. There's the formation of zinc oxide, and the copper-zinc alloy is largely decreasing. And very interesting, there's a small remainder in the spectrum that we couldn't assign to zinc oxide or to zinc copper alloy, yeah? And the spectrum actually is that of zinc formate. Yeah? So we can have a very low fraction of zinc formates that we see. So we actually see that under these conditions, yeah, very rapidly we have the formation of zinc formate. Yeah? So the Sitka showed us that that's the reactive intermediate. The X-ray absorption tells us it's associated with the zinc oxide. Copper is always present in a metallic form. The zinc is partially reduced after reduction, yeah, so we have a copper-zinc alloy to start with, and this actually is rapidly, partially reverting back into zinc oxide, and there's the zinc formate forming. Yeah. So under reaction conditions, if we have the copper-zinc alloy, yeah, this is to a large extent lost, yeah, because of the reaction with CO2. With CO2. The formate is the reactive intermediate, and the formate is associated with the zinc oxide. So what about palladium on zinc oxide? Yeah, is this system similar? Do we have a metallic phase? Do we have an alloy phase? Is there a role of the zinc oxide? And to do that, we synthesized colloidal particles of palladium, so there is a relatively well-defined particle size distribution that are impregnated on zinc oxide. So here we have particles between 1 and 2 nanometer on zinc oxide. And we look for the catalytic conversion there, yeah, as function of temperature, high temperature, lower temperatures. Yeah, and then on the left in black is the productivity. This actually is a very productive catalyst for this reaction. And on the right in blue, we have the methanol selectivity. And then as function of temperature, there is a selectivity of slightly below 70%. And at 220 degrees, the selectivity of methanol goes up to about 85%. This is a very highly active and a very selective catalyst for this reaction. Certainly at the selectivity is very good at certainly the lower temperatures. So if we do the same switching experiment with carbon dioxide 12 to carbon 13 carbon dioxide, the formate starts rapidly forming. So that's very similar to what we've seen in the copper zinc oxide system. Because we see something very similar, we assign here the formate to the zinc formate based on the previous experiments that we did. If you do the isotope switch, you see very similar things that we've seen before. There's a very rapid disappearance of the formate carbon 12 and the appearance of the formate carbon 13. So it's really the reactive intermediate in this system. So it behaves very similar to the copper zinc oxide system. Then we did, of course, the X-ray absorption under very similar conditions, high pressure, first reduction of the system, and we measured the structure of a palladium zinc after reduction. So that's the blue line that we have here. After switching on the carbon dioxide, so we went from reducing conditions to catalytic conditions, the spectra didn't change. So here, in opposite to the copper-zinc system, the palladium-zinc, the alloy is stable under catalytic conditions. So here I have a alloy on the surface of zinc oxide that's actually a very active selective catalyst for methanol synthesis from carbon dioxide. So then, of course, the question is, what's the role of the alloy? And what's the role of the zinc oxide? That's still not really clear. So we try to use a little bit of smart synthesis, where colloidal particles of palladium zinc are synthesized and they are impregnated on an inert support, both on silica and on alumina. And in one of the systems, we added zinc oxide as a component. So we have a system where we have palladium zinc alloy particles on an inert support, and we have those particles in the presence of zinc oxide. And if you look to the catalytic performance of that, if you have the palladium zinc on silica, this is under these conditions active in carbon dioxide conversion. However, the selectivity to methanol is really, really low. So these particles are unselective for methanol. Same thing if you put them on alumina, where the catalyst is slightly more active, but also there the methanol selectivity is really low. And only in the presence of added zinc oxide, where the activity of the silica system goes up a little bit, but definitely the selectivity goes up way, way more. So the system is really only active and selective in the presence of zinc oxide. Palladium zinc itself yields carbon monoxide, and palladium zinc in the presence of zinc oxide is yielding methanol. So what's the role of the alloys? Copper zinc is unstable under catalytic conditions. Palladium zinc is stable, but palladium zinc only is producing CO. It's only selective in the presence of zinc oxide. So it's the zinc oxide that induces selectivity to methanol, and it's actually stabilizing the formate as an intermediate. So the active intermediate, wherever it's formed, it ends up on the zinc oxide, and there it's the precursor for methanol. So if I now summarize all this, that under catalytic conditions, I have a formate on the zinc, which we think it's on the zinc oxide. Of course, if you add the hydrogen there, and it's the copper zero surface that actually helps split the hydrogen, that's how you can form methanol. And of course, if you bring this system at higher pressures of hydrogen or in vacuum, you start forming the copper zinc alloy. If you bring this system in carbon dioxide only, you make zinc oxide and copper. If you bring this into oxygen, you make zinc oxide and copper oxide. So again, depending on the conditions, you end up with something very, very different. And of course, within the catalytic cycle, you have the formate. You hydrogenate this, making methanol, and then on the zinc oxide are you reforming back the formate. And of course, how that exactly occurs here, there is still much work to be done. So the system is, I would say, a beautiful multi-component catalyst here where the multiple components are actually contributing, co-contributing, having a large synergy. So let me now go back to the in situ operando. Again, let me summarize. The catalyst structure is a function of its environment. And the premise that comes with that is that only the structure that we measure under reaction conditions can give insight into its activity. Keep in mind that conversion is changing the composition of a gas. The pressure gap really is a materials gap. So the last slide. If we try to understand how a catalyst functions under industrial relevant conditions, as I said, the industrial catalyst is a very complex material. So to really understand all aspects of that, there is many things that we need to understand. And of course, if I start in the left bottom in this figure, where I have on the x-axis the proximity to the conditions of an industrial process, And on the y-axis, the maximal achievable knowledge of this catalyst. If you work under relatively simplistic, simple, low-pressure conditions, there's a lot of information that you can get. But of course, to what extent that knowledge adds up to understanding the actual system, it may not be there. If you change your conditions into a new regime, you make a step function. So it's not a continuous line towards understanding the complexity. If you change a fundamental step in your system, you have a step function in the amount of knowledge that you can gain. And of course, there's many steps that you need to make before we really understand the functioning of a real catalytic process itself. Same thing if I talk about materials. If I look to a model material, I learn a lot about this model material. If you have a metal only, and if you start adding components that mimic a support, you have a step function in the understanding that you can achieve. It's not a continuum. And why are we stressing this so much? And that is because you should be careful how you extrapolate your results. I think you should not extrapolate beyond the discontinuities in the knowledge that we can get. So this work was done over many years by many people, and specifically like to thank Maxime Sabilski. He's a postdoc currently with Clariant, who worked very much on this. Arik Beck, who was a PhD student. Andreas Brenik, who is a current PhD student who helped with current measurements. I think Mark Newton, Vitalis Juskevich, Dennis Palagin, who are postdocs and scientists in my lab, who had really essential contributions in this work. I'd like to thank Leon van der Water from Johnson Matthey for his perspective on the copper zinc oxide on the alumina system. Gerhard Mestel for his continued support and his interest in what we do. And then of course there's more people. Mark Wielinger, who's now in TUM for the electron microscopy that we did on the system. Same for Frank Kroemeijer. And of course Maarten Nachtegaal, Olga Savonova, who are the beamline scientists at the Swiss Light Source. And without these people, we wouldn't be able to do these beautiful results. So I really enjoy collaborating with those people. Swiss National Science Foundation, the ETH and the Polish Institute are thanked for their funding over the years. And of course, the many beamlines that we go to, but here specifically I'd like to mention the Swiss-Norwegian beamline at the ESRF and the Superexas beamline at the Swiss Light Source. And I thank you very much for your attention. Thank you.